Hello everyone. We're going to continue our discussion regarding exponents, base 10, and something called scientific notation. So as you notice on the left side of the chart, we have positive exponents, powers of 10, and they represented the amount of zeros after the 1. Right? And we have the billion, million, billion, and trillion, and it can obviously go larger. And then we have the negative exponents, which represented the very tiny, tiny pieces of our world. So 10 to the 1 is 0.1, 10 to the negative 2 is 0.01, 10 to the negative 3 is 0.001, and so on. There is a connection with the exponent, as well as the zeros here. So you could say that negative 1, there's 1 0, right? It's the whole number. 2 zeros, including the whole number. 3 zeros, because it's including the whole number. The only issue with that statement is sometimes we don't need to write the whole number. 0.1 is also the same as just 0.1. So really, what this exponent represents is the number of spaces from the decimal point. So 1 space, 1 exponent. Exponent of 2, 2 spaces. Exponent of 3, 3 spaces. Exponent of 4, 4 spaces. And so on. 1, 2, 3, 4. Okay. All right. Again, base 10 makes up our world. Base 10 is what we use for our number system. In computer science, that's base 2, binary. But here, in the real world, we talk about base 10. I want you to take a moment and I want you to, I want to take a moment and I want to use what we have right here and I want to rewrite these numbers in standard notation. So before we had exponential notation, and now we wrote them in standard notation, which is their normal number. I want to do the same here. So we have 3 times 10 to the 9th. That is 3 times 1 billion. And that, of course, is going to be 3 with 9 zeros. What about 4 times 10 to the 3rd? It's also 4 and 3 zeros, right? That's 4 times 1,000. It's 4,000. What about 1.2 times 10 to the 6th? 1.2 times 1 million. It's 1,200,000. Not 12,000. 12 million, sorry. It's 1,200,000. What about 2.6 times 10 to the 5th? Yeah, it's 26,000. Sorry. $260,000. Then we have 2 times 10 to the negative 4, so it's 2 times 1 over 1,000. 10,000, which is 2 over 10,000. How could we write that? Two 10,000ths, right? For 6 times 10 to the negative 6, what would that be? You guys can, of course, use your calculators for this. That would be 7 over 1 million. B. So if we use our calculators and we rewrote these in standard form, it would look something like this. There is a connection between the exponent and the number in standard notation, right? One thing is that when we multiply by a power of 10, the amount of digits increases, right? The number of digits increase. If it's a positive exponent, it gets farther away from 0. If it's a negative exponent, it gets closer to 0. Right? So we have 10 to the 9th. That 9 represents the number of spaces after 3. Okay? Where's the decimal point in the number 3? There's an imaginary decimal for every whole number. Where is it? It's right to the right of it. And if we take that decimal and we count the number of spaces to the right, it should be match the exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing over here. If we locate that decimal point and we count the number of spaces to the right, 3 is the same as our exponent. Same is true as for 1.2 times 10 to the 6th. So if we have our decimal point is between the 1 and the 2, 1, 2, 3, 4, 5, 6. And it works for the rest. For negative, it goes the other way. The decimal point goes to the left. So if we count the number of spaces from the right side of our whole number, we'll count the number of spaces. 1, 2, 3, 4. Same thing with 7 times 10 to the negative 6. 1, 2, 3, 4, 5, 6. So we can actually write this without using a calculator if we know how many spaces we need to move left or right from the decimal point, depending if our exponent is negative or positive. All of these numbers, all of these expressions, is something called scientific notation. Scientific notation allows us to write really large or really small numbers in a more condensed way, used often in sciences like astronomy and biology. This is our definition. A positive finite decimal s is said to be written in scientific notation if it is expressed as a product of d times 10 to the n, where d is a finite decimal, so that 1 is less than or equal to d, and d is less than 10, and n is an integer. The integer n is called the order of magnitude of the decimal, d times 10 to the n. Are the following numbers written in scientific notation? So let's break down this definition first before you answer that question, right? It needs to look like this. It needs to be d times 10 to the n, where d is a number. It's a decimal, right? It's a decimal, and it's a finite decimal. That means it does not go on forever. Finite means stops. It stops, right? If it was an infinite decimal, that would be like 0.3 repeating. That's not what this is. This is d times 10 to... It goes in the form of d times 10 to the n. D is just a decimal. Could be a whole number. And it must be less than 10 and greater than 1. That's what this phrase here, 1 less than or equal to d less than 10 is. D, the number in front of the power of 10, must be in between 1 and 10. It can be equal to 1, but it cannot be equal to 10. So it has to be a single digit whole number, but it can be a decimal afterwards. So here we have some options. We got A, B, C, and D. The finite decimal 234 567 thousandths is equal to every one of the following. So if we actually used a calculator and we typed in all of these choices A, B, C, and D, we would get 234 567 thousandths. But which one is represented in scientific notation based on that definition? Remember, the letter D represents the decimal, and it must be in between 1 and 10. 10 to the n is any integer, so negative or positive. Which one is it? Unpause the video when you're ready. Yeah, it's A. It's A. Let's go through why it's not the others. It can't be B because 0.23456 is not a number between 1 and 10. Nope. C. For the same reason, 234 8.567 is not in between 1 and 10. And lastly, the same reason that is not between 1 and 10. A is our answer. I want you to take a few moments and I want you to write the following in scientific. I want you to identify if the following is written in scientific notation. So, you're going to identify if it's correct or incorrect. That's it. Are the following written in scientific notation, yes or no? So for exercise 1, is that written in scientific notation? It is. Our numbers are, it's because 1.908 is between 1 and 10. I want you to do the same thing for exercise 2 through 6 on your own, so pause the video. So I want you to identify if it is a scientific notation or not, and follow up with a reason why it is or why it is not. When you're ready, unpause the video and we'll go over it. Okay, exercise 2 is not. That's because uh, 0.325 times 10 to the negative 2 is not written in scientific notation. Because 0.325 is not between 1 and 10. Exercise 3. It is correct. Scientific notation. 7.99 is in between 1 and 10. Exercise 4. Not correct. 4.0701 plus 10 to the 7th is not written in scientific notation. Because we are adding the power of 10. Right, we're supposed to be multiplying. 5 is not correct because 18.432 is not in between 1 and 10. Exercise is correct because 8 is in between 1 and 10. Well done. For your activity for today, I want you to complete these two activities. So you're going to determine the smallest object to the smallest object. Largest to smallest, smallest to largest, right? So here we have one about planets and the distance from the sun. And below we have other objects that are really small, like pollen, bacteria, cells, and you're going to be writing that in order of size, right? So you're going to identify here what the largest number is and what the smallest number is, and you're going to order it in that way. Same thing with number 2. You're going to identify which one's the smallest, which one's the largest, and you're going to order it in that way as well. And that is it. Have a wonderful day.